Right, good afternoon, everybody. I hope everybody is suitably wired with caffeine after the coffee break, and you're all ready for the final stretch of the day. Hopefully I won't put you to sleep, but yeah, you're welcome to throw stuff at me if it gets too boring. Okay, so today my talk is about Valhalla, bringing the JVM into the 21st century. First, I want to start with a bit of a disclaimer. None of this that I'm talking about here is final. Okay, so Valhalla is still very much early access at this point in time, and chances are pretty good there'll still be some changes. And anything I say here may change, so just keep that in mind. A little bit about myself. My name is Julian Exenberger. I'm consultant at Capgemini from my, as you might see from my oversized T-shirt. Best way to contact me if you want to connect, I'm on LinkedIn. And this is my 24th year coding Java. I felt very old today because one of my colleagues informed me that he is 24 years old. All right, so he was born when I actually started getting a paycheck from Java, so that's always good. And in the vein of talking about old stuff, I'd like you to cast your mind back to the year 1995. All right, so hands up. Anybody want to take a guess about what's important about the year 1995? That's it, yeah. Java is released in May of 95. So we're actually now less than a year away from Java's 30th anniversary. Which is, it's quite a thing for me, right? Because in my mind, when I think about a 30-year-old computer, this is what I think about. And the reality is that, oh, it was supposed to change. Oh, there we go. The reality is that this is actually what a 30-year-old computer looks like. And what makes it even worse, oh, come on, man. Delayed reaction, thanks, Apple. So what makes this even worse is this was actually my computer from 30 years ago. So what have we got here? AMD 486 DX4 100. 8 megs of single inline memory module RAM. Okay, who remembers those? Yeah. To all the gray hairs, yeah. I had for the time a massive 1 gig hard disk. Okay. Double speed CD-ROM, both the stiffy and the floppy drive. And of course, what was obligatory for this time was a Sound Blaster 16. For those of you old enough to notice, there is no mention of a video card because back then, well, everything was 2D, so it didn't really matter that much. And of course, when Java was released, the last thing that I was thinking about was writing very fast Java programs on my middle-of-the-range PC. My focus was definitely on other things, such as what's behind me. Okay, so where have we come in almost 30 years? So the average CPU today is 4,500 megahertz, or 4.5 gigahertz. So that's a 45-time increase from 1995. In terms of hard disk, and I would actually say this is going on the small side these days, you've got 512 gigs compared to my 1 gig. But the biggest increase actually is the memory. I had 8 megs, and these days you start off at 8,000 megs or 8 gigs. So that's literally 1,000 times more memory than what I had on my PC. Now, I don't really want to talk too much about capacity. What's actually more interesting for this conversation is relative memory speed. So in 1995, the speed of my memory was roughly 66 megahertz. So if you think that I had a 100 megahertz CPU, the difference in access time and operations, both on the bus and on the memory itself, was roughly about 33 megahertz. If you compare that today, you're talking about at least 1,000 times slower than your average CPU. Okay, so 3,200 megahertz DIMM, 4,500 megahertz CPU. Imagine, if you think about this in relative speed, imagine driving at 30 kilometers per hour versus driving at 20 kilometers per hour, and then driving at 300 kilometers per hour versus driving at 200 kilometers per hour. And that's pretty much the relative difference you have in memory access speed today. So why is this important? In 1995, your memory access speed was not so much of a bottleneck. It was obviously slower, but relative to what we have today, it was not quite the impact that you see. So why is this important? Let's pretend for a moment that you are building a piece of furniture. So you've got a warehouse that's full of lumber, all ready for you to go and make your piece of furniture. Then you have a very, very large bench that you use to actually go and do all the work, construct your piece of furniture on. I'd like you to just think for a second, or imagine for a second, that your warehouse that's full of lumber is your memory, and your bench is your CPU. Okay, so think for a second, what is the most logical way that you are going to build your piece of furniture? All right. So to quote Mr. Spock, logic dictates that if you have a very, very large workbench, you're going to fetch as much wood as you can from your warehouse, bring it all, stick it on your CPU, on your workbench, and then do all your work. So everything's there for you. It's very efficient for you to go and do that. Okay. In computing terms, you can think about this as how your CPU and your memory works, right? So your workbench is your CPU, and your warehouse with your wood is memory. So ideally what you want to do is you want to take as much stuff from your warehouse, put it on your CPU, work with the registers and the caches that are on your CPU, and then write back to memory when you need to. Of course, there's a problem, because that's not how Java works. Okay. In Java, we have the heap and the stack. So your heap, which is normally stored on your RAM, is, of course, where all your objects are stored. So instance of an integer, your optionals, your strings, your own custom classes are normally stored on the heap, which is accessed in your main memory. On the stack, which is closest to your CPU, what you mostly have are object pointers and primitives. So in Java, you've got this wonderful problem that when you access your objects, it's literally like you go from your bench, every time you access the object, go walk down to your warehouse, go fetch a piece of wood, bring it back to your bench, do your work, take that piece of wood, put it back in the warehouse, take the next piece of wood, and bring it back to your workbench. So I don't want to really point out the obvious here, but this is a problem. So how do we solve this problem? Okay. And this is where Project Valhalla actually comes in. So the mantra of Valhalla has always been codes like a class and works like an int. All right. If you think about this, we want to have the expressiveness and power of being able to write objects in Java because it's a programming language. But it would be really great if we could actually have some of the performance benefits of a primitive like an integer. Of course, primitives were always a trade-off in Java. Back in 1995, before JITs, before the optimization you got, the only way to get any performing arithmetic operations was to have these primitives. So it was kind of a trade-off. Okay. And the class world and the primitive world have always been separated. So the idea behind Valhalla is actually to fix this. How do you unify classes and primitives so that you get the full power of OO, but at the same time you've got the performance of your primitives? Okay, so I'd like to ask a question to the audience. Who here has worked on a project that has taken more than 10 years to deliver anything?
The first or the last piece of work?
The first piece of work. Okay, so it's been going for quite a while, to say the least, and we'll talk a little bit about this later. But what is Valhalla actually trying to do? Okay. Let's look a little... Oh, come on, Mac. All right. Anyway. As we said earlier, we want to bring as much as we can onto the CPU. So we want to take advantage of our very big workbench, which is our CPU. And we want to be able to bring objects closer to essentially our stack. In order to do this, we've got to give the VM options about where an object lives. So if you think about one of the problems with objects, if you think about your memory as almost like one big map where the value or the contents of your objects are stored in memory, and you've got a key to that, which is your object pointer. Okay. If you're copying around your object pointer, the pointer still has to point to the right place in memory. So one of the constraints that Java has always had is because you've got this identity around an object, and you're copying around the identity, you have to make sure that the object stays in the place that you're referencing with that identity. So you have to get rid of identity. Okay. Now, what is identity? If you're just a layman Java programmer, if you've ever coded equals equals versus dot equals, when you're doing equals equals, of course, you are comparing your object references. So if that object pointer is pointing to the same location, then the objects are reference equals. And of course, dot equals does a content comparison. So there you're actually comparing the fields of your object. This, of course, leads to some interesting bits of behavior. You can go in Java, it's quite legitimate that you can go new integer 5, or x equals new integer 5, and y equals new integer 5. And then if you do x equals y, there, of course, won't be equals because they're pointing to different instances. So how do we resolve this? The biggest piece of Valhalla is essentially the value class. All right, now what is a value class? Let's take this rather contrived bit of code that I have here. It's a class called test value, and there's nothing in it really. I've got a main method which basically just loads instances of test value into an array of 1 million. How do we change this into a value class? Well, we add the value modifier in front of class test value. Okay, so right, we're done. Talk over. We can all go home. There is, of course, more to it. So what does the value indicator actually do? The obvious thing is that it tells the JVM that this class does not have any identity. And with that comes a couple of constraints that you need to put on the class in order to make this a true value class. So for one thing, all the fields are effectively final. Right? Your class becomes immutable. This has a downstream effect that you have to limit your inheritance because obviously you have to extend classes that are either themselves value classes or are effectively value classes. So they're also immutable. And because you no longer have this concept of an object identifier, when you do equals equals, what you're actually doing is you're comparing the fields inside the classes. So that means if assuming integer was a value class and you went x equals new integer 5 and y equals new integer 5, if you do x equals y, they will actually return true. So I'd like to make one point about records. So if you've been using records, obviously they're also immutable. There's a lot of constraints on them that seem very similar to value classes, but I want to just make a point that records aren't value classes, but a lot of records could be value classes. Right? So there's a lot of those are actually candidates for good value classes. Now, if you have immutability, you don't have to worry about pointers. It means that the JVM can literally take this piece of class and copy it around as it sees fit. Because you can be guaranteed that if you copy an instance of this object, that equals will always be true, and you don't have to worry about the class changing underneath you. And if you make copies of that, then everything lines up. So if you look about what you can do scalarization of a class. And this is effectively where we take a class and flatten it, tear it apart, and put it onto the stack. So if you take this value class record here, value record of point int x and y, you can now take this and push the values x and y onto the stack. So no more having to go to memory, your entire object is actually available for you on the stack. There's some interesting benefits from this, because if you make a copy of record, you can actually just pass around the registers if you're looking at it from an assembler point of view. And it means you can actually make copies of objects or value objects anyway that are almost zero cost. And of course, this all took 10 years. All right, so 10 years and all we get are one lousy keyword. A comment by Brian Gutz when he announced this project at Java 1 2014 is, do you realize you've signed yourself up for 6 PhD theses? All right, now what you see here has gone through quite a few iterations, and one of the problems always with Java is that if you make any type of change like this, is that Java that's written, or a Java class that's written for Java 1.0 still has to run on your shiny new Valhalla-enabled JVM in 2024. And on top of that, you need to create a model that fits into the programming language and then actually delivers a relatively decent developer experience. And this really has been the challenge in getting Valhalla out. So if you want to look at a brief history of Valhalla, started out with a paper by John Rose on generic specialization in 2014. This led to a couple of prototypes in that time frame. Then they started looking at a couple of prototypes around adding new bytecodes into the language, into the JVM. And the last one, the L world, values as references, is a version that I did a presentation on. And then just as I finished the presentation on, they canned the whole thing and reverted to the model that I've just presented to you now. Now, the thing is that each of these prototypes had their pros and cons. And either you're adding a lot of new complexity into the JVM with things like bytecodes, or in the case of number 4, the L world references, you're adding a lot of complexity to your developer experience. So the challenge of Valhalla is, how do you add this complexity or this change without killing your developer experience? And this has led to where we are now. You've got a lot of work that's been done into something that looks like actually a very simple change. Also, in the meantime, in this 10 years, you've also had a couple of other initiatives in the JVM that's actually aided in getting Valhalla out. So you've got flexible constructor bodies, which has fixed some of the semantics around initializing classes, and then also null restricted and nullable value classes, which has helped to look at how objects are initialized. So, where to from here? JEP 401 is early access is available today. You can go to the website and download it. This first iteration will bring value classes to the JVM as well as some basic scalarization. So there's going to be some types that are converted into value classes, and there's going to be some basic optimization that's done. And of course, as we get iterations of Java, these optimizations are going to increase. Obviously, at some point, it's got to get released into the main JDK, and of course, there is no date on this, right? So it could be next year, it could be in 2 years or 5 years, I don't know, but it has to happen at some point. We're also going to get enhanced primitive boxing. So what is enhanced primitive boxing? Essentially, what it means is that you can take a primitive and you'll be able to treat it as a receiver. So the JVM can take one, box it up into an integer value class, and then you can call toString on it. Looking a bit further down the line, the original goals of Valhalla was to fix generics in Java. And one of the first things to fix is obviously the ability to add primitives to generics. So that is where you can create a list of type int as opposed to just being forced to create a list of type integer, which we can't do at the moment. Further down the line, we then want to do reified generics, and that is where we actually ditch type erasure. So as you probably know, in Java, if you do generics, the actual generic information that's carried is erased when you compile it, and at runtime, that information's not there. So if you've got a method that takes a list, you can't create two methods, one which takes a list of string or one which takes a list of integer. It won't compile because from the perspective of the JVM, those are it's just a method that takes list. And then finally, if you are going to create value classes, and one of the big applications of value classes is, of course, the fact that you want to create arithmetic, or classes that model arithmetic values. Right, so who here likes working with big integer and big decimal? You like it? Wow. Okay. Who wishes they had plus and minus on big decimal and big integer? Yeah. Okay, so the good news is that the Valhalla team is actually looking at this. They realize that if you are going to create arithmetic classes, it would be really nice if you had a little bit of operator overloading. What that's going to look like, I don't know. They're talking about it. It's just nice to know that they're actually considering it. Okay. Questions? Yeah.
I was a bit surprised about the syntax since regularly equals compares memory locations and dot equals compare contents. I would have sort of expected that the equals would be forbidden and everything would be dot equals. So is there a situation in the new Valhalla where equals and dot equals are not the same?
I mean, are you talking from regular classes or specifically from value classes? That's a good question. I mean, I would imagine that they would always be the same. I mean, the logic behind it, if you think integer 5 and integer 5 should always be the same.
Yeah.
Okay.
Would it be more logical than to forbid the equals?
To the same. Or just like an alien, or at least actually the same.
Yeah. I don't have the answer. But yeah, maybe if there's somebody from Oracle. Yeah.
So I can't speak for the OpenJDK project. I'm not even a member of OpenJDK. I think the reason why equals equals will stay valid is because you never know whether you have a value or an object, right? You don't want the JVM to crash or throw an exception just because you happen to have an object and a value and you want to do an equal-equals comparison. I'm not sure about whether it would be possible to still override equals, because I think it will be, right? I think equals sign will always do all fields, but you can still implement an equals method that just does a subpart of that. I think that's...
Well, it's, if I understand correctly, it still extends object, right? So it must be able, you have to be able to extend equals.
Yeah. I mean, yeah, the question is whether the equals sign then delegates to that, but I don't think it does. I think the two equal characters will always do a full field comparison.
Yeah.
If you happen to have like a more suitable equals implementation, you can use that for, I don't know, sets or whatever.
Yeah, absolutely. Look, I mean, it's still valid to do both, if you think about it, right? I mean, if you extend equals, you have a semantic that you have to adhere to, and that doesn't change for value classes. The big change really is equals equals. Any other questions? Yeah?
How does that work with non-primitive types? Because if I create a value class which contains a string released, what is the actual benefit? Because these are still references.
Look, I mean, so the benefit is that you're giving the JVM options on how it optimizes that, right? So if you've got a very simple class like point, in my example, that's very easy to flatten, right? In more complex cases like that, it's up to the JVM to decide. So like for an array of char, it might be possible to actually flatten that because you know what the constraints are of your array and you can actually make determinations about how it should be on memory. But yeah, I mean, in certain cases, it actually doesn't make sense to have a value class and it just have a normal class in those cases. Okay, all you're getting with value class fundamentally is that the JVM can now make decisions about how it optimizes things. So,
Are there plans to migrate some of these classes to value classes?
yes. So most of your primitives, your standard primitive wrapper classes, so Java lang, integer, float, long, etc., those are all candidates, and Java optionals.
Right now you have escape analysis, which already does optimizations like that, right? So can it do more than just what escape analysis can do?
Look, so there's a lot that's already done with escape analysis, but eventually you need types. You know, so same thing with a dynamic language. You can get to a certain point with your optimization, but you need that type information to go further. So the thing with value classes is it's not just the value indicator, it's also the semantics around it. So the fact that it's immutable, the fact that there's no identity gives the JVM more options in how it chooses to do that analysis. It can do more, basically, with that. So in cases where it can't actually correctly infer, if it can do escape analysis on that, the value class gives it additional information that confirms that it can do that. Okay. Any other questions? Yeah?
Yeah, actually, in addition to the answer to the previous question, I believe it's also a big value that you would be able to use a value class as a member of another class, or as an element in an array, which gives you an array of all these class instances, so you don't have all these references over there. You just have a linear block of memory with pairs of numbers, for example.
Yeah.
That's, well, I mean, that you cannot do with escape analysis.
No, well, exactly. Right. So, I mean, you could probably do it on very simple classes. Like, and if you know the exact scope of that class. But yeah, I mean, again, it goes back to why you need the value class. It's really to be able to give the JVM the information that it can do that type of optimization. Yeah.
And why don't you just use a memory pool on the stack for smaller objects that's short-lived? Then you don't need the word value type, right?
Well, again, it goes back to that. It's like you need to be able to make those inferences on the object. Okay, now maybe you can do that with simple classes, but as soon as you've got a complex class, how do you know what the extent is of your object? You know, so like the safest thing always then to say is, okay, I'm not going to try flatten this, just leave it on the heap. And again, with value classes, it makes it explicit. You're explicitly saying that the JVM's got the option to actually scalarize this and put it onto the stack, or even into like your L1 and L2 caches if you want to. Any other questions? Yeah.
Are there any projections about performance improvements in specific types of applications?
Brian Goods did a talk at DevOps, don't ask me how you pronounce it, where he showed some improvements in some of the performance numbers they're getting. Obviously, nothing is final because they don't have a final version of what this looks like, but there's definitely an improvement. Okay, I mean, if you think about it, if you're doing like a lot of integers, or like the example I showed you, basically all that whole array of 1 million classes could in theory be inlined on your stack. Whether or not it would do that in that example, I don't know, but that's possible, right? So you literally have new objects that they never hit the heap, they never have to be garbage collected. They basically live and exist within that stack frame. Okay. Yeah.
Are you protected against, for example, in C++, you could accidentally forget to say new, and then you combine something from the heap and the stack, then it's gone later on because it's been popped off the stack. Are you protected by Valhalla by such an incident? Is it like, can you combine heap and stack-based allocation?
No. Look, you're protected from that, right? So again, it's like your references, if you can have a reference inside your value class which points to the heap. But that's just the object pointer that's part of your value class. I'm not sure if that answers your question.
Yeah.
Okay. Okay. Right, so in closing, you can go take a look for yourself. Like I said, the EA is available today, so it's JEP 401. If you want to go a little bit more into the details, there's this talk that I mentioned earlier on DevOps by Brian Goods, and he goes into a lot more detail about how they actually got to a working prototype of Valhalla and how they've gone through like all these complex prototypes and then got to a point where they actually have a very simple model, and that's the model that I presented now. Okay, thank you very much, and I hope you enjoyed the talk.